In this video, we will do a harder infinite limit example. So the question says we want to find the limit as x approaches infinity of the square root of 16 e to the 4x plus e to the 2x minus, outside of the square root, minus 4 e to the 2x. Okay, so to get started with this, we might plug in infinity and see what happens. So we'll get 16 e to the 4 times infinity is infinity, and then plus e to the 2 times infinity is also infinity. It's the square root of that whole thing. And then minus 4 e to the infinity as well. So we need to know what e to the infinity is. And there's a couple ways we could sort of logic that out. One is, if I remember my graph of y equals e to the x, that graph has this shape, this exponential growth graph. And as x goes to infinity, as my x values get really, really, really big, going this way, my y values also get really, really big. So e to the infinity is going to be infinity. Another way I could reason that out is e to the infinity means e times e times e times e a bunch of times, an infinite number of times, and that's going to be infinitely big. All right, so we have the square root of, this is going to be 16 times infinity, which is infinity, and then plus infinity, which is just going to give us infinity inside of that root, and then minus 4 times infinity is infinity. The square root of infinity is still huge. That'll be infinity. So we get infinity minus infinity. And infinity minus infinity is in indeterminate form. I cannot just say it's 0 because these infinities don't necessarily have exactly the same size. When I write infinity, that just means it's getting really, really big. But it could definitely happen that one of these infinite terms is getting bigger a lot faster than the other one. All right, so at this point, I want to give you 6 minutes to try the question. So pause the video for 6 minutes and see what you can do from here. 4, 3, 2, 1, pause it and try this one for about 6 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 6 minutes. Let's talk about it together now. So I'm going to do this in 2 ways. So the first way I'll call attempt 1. And in attempt 1, I'm going to use my idea from previous infinite limit examples, where we factor the dominating terms. We are going to factor the dominating terms. Okay, so we have the limit as x approaches infinity. So inside of the square root, the dominating term as x goes to infinity is going to be e to the 4x. That exponent is going to be the biggest, so that term is going to dominate. So let's factor out e to the 4x. And that'll leave me with 16 from the first term. From the next term, I'll have the e to the 2x, and then divided by this e to the 4x that I'm factoring out inside the square root. And then we have minus 4e to the 2x. Now we have the limit as x approaches infinity. Let's split this square root up into the square root of e to the 4x times the square root of 16 plus. And I could simplify e to the 2x over e to the 4x. That becomes 1 over e to the 2x when I subtract those exponents, and then minus 4e to the 2x. So I can simplify the square root of e to the 4x. This is just e to the 2x, because e to the 2x times itself is e to the 4x. One thing that I might be thinking of is, wait, sometimes when I square root something squared, like square root of x squared, I need an absolute value on that. Because the x squared is going to make it so that all these outputs are non-negative. And if I didn't have those absolute values, the x could have negative outputs. So putting the absolute value will fix that. Sometimes I don't need an absolute value, because if I had something like square root of x to the 4th, I might think, wait, that's x squared. With this, I don't need to put an absolute value around it, because x squared is already guaranteed to be non-negative because of the squared, that even power. With e to the 2x, we similarly don't need an absolute value, since e to the 2x is already non-negative. One of the ways I can see that is if I look at this e to the x graph over here. E to the 2x's graph is really similar, but notice that the y values are never negative, because e to any power Can't be a negative number. All right, so let's continue to simplify. We have this limit as x approaches infinity. And now let's factor out the e to the 2x's. So there's an e to the 2x here, and there's an e to the 2x here. Let's factor those out. That'll leave me with root 16 plus 1 over e to the 2x, and then minus 4. And now let's plug in. That'll give me e to the infinity first, times root 16 plus 1 over infinity is 0, and then minus 4. Okay, and e to the infinity is infinity, and then we'll get 4 minus 4, which is 0. Okay, and it might be tempting to say, wait, 0 times anything, isn't that just 0? I have to be careful though. Infinity times 0, let me say it like this first. This is actually, when we write this, it actually means, so the infinity means we have a huge number. And when I write 0 like this, it doesn't mean it's actually 0. It just means it's getting super, super close to 0. It's getting really close to 0. So it's just a super small number. And when I multiply a huge number by a super small number, that doesn't necessarily have to be getting close to 0, because maybe the huge thing is growing a lot faster than this thing that's getting close to 0 is getting small. So infinity times 0 is an indeterminate form. We've actually seen that before, but I wanted to just give some intuition behind why. Okay, so unfortunately, we factored out this dominating term, and we got it to a point where I have infinity times 0, which is indeterminate, which means I'd have to simplify, but we were kind of simplifying. So this leads me to a dead end. So let's try this in a different way. All right, so I'm going to call this attempt 2. In attempt 2, I'm going to recognize that in my original problem, I had the square root of stuff and then minus something. And one of our techniques that we have used to simplify something like that is the conjugate. Okay, so let's see what happens if I use the conjugate. So our original limit was as x goes to infinity, square root of 16 e to the 4x plus e to the 2x minus 4e to the 2x. Okay, so let's put a big old parentheses around this, and let's put it all over 1, so that I can multiply the top and the bottom by the conjugate. So the conjugate is going to be 16e to the 4x plus e to the 2x, square rooted, and then plus 4e to the 2x, divided by itself, root 16e to the 4x plus e to the 2x, and then plus 4e to the 2x. All right, so we get the limit as x approaches infinity. So on the numerator, that's where multiplying by the conjugate is really helping. It'll give me this first term squared. When I square that square root term, it'll give me 16e to the 4x plus e to the 2x. And then I'll get minus this next term squared, that 4e to the 2x squared. Okay, and that is going to be 16e to the 4x. All right, all over the denominator. 1 times this other stuff is just that stuff. Root 16e to the 4x plus e to the 2x, close that root, plus 4e to the 2x. Okay, if you're a little bit unsure of how I got that numerator, I would encourage you to pause the video and just quickly multiply out the terms in the numerator to check that I get this. Okay, so these 16e to the 4x's, they cancel. And now, let's just quickly see what happens if we plug in. If I plug in on the numerator, I'll get infinity. On the denominator, inside of the square root, I'll get an infinitely large thing. And when I square root that, that's still infinity. And then I have plus in this other term, 4e to the 2x. That'll be infinity. So I have infinity over infinity, which is still indeterminate. So I need to simplify. But luckily with this, I can still simplify it further, because with this, I can now factor the dominating term. Okay, so we have this limit as x goes to infinity. I have that e to the 2x on the top. On the denominator from the square root, Let's factor out e to the 4x. And let's just separate that as well. Square root of e to the 4x times the square root of the stuff that's left over, which is going to be 16. And then plus, from the next term, I'll have 1 over e to the 2x. So that simplification we've done before in attempt 1. Okay, and then plus that 4e to the 2x term. All right, and now square root of e to the 4x, we've seen from above, this just equals e to the 2x. I don't need to put an absolute value around it because e to the 2x is already going to be non-negative. Okay, and now I see e to the 2x here, I see an e to the 2x here. Now we can factor those. So we get the limit as x goes to infinity, e to the 2x on the top. And on the bottom, if I factor out that e to the 2x, I'm left with the square root of 16 plus 1 over e to the 2x. And then plus 4. All right, and now the e to the 2x is canceled, so that's nice. And now let's plug in. We get 1 on the top. Over, on the bottom, we'll get root of 16 plus 1 over infinity, which is getting close to 0. And then plus that 4. So we get 1 over 4 plus 4, which is 1 over 8. And that is our answer. So one of the morals of this example, one of the things that makes this one more challenging, aside from the fact that the function itself is just a little bit more complicated, is we had to try it in multiple ways. We did this attempt number 1, and initially just by looking at it, it wasn't totally clear whether or not that first attempt would help. We tried it, it kind of led us to a dead end, and then we had to try something different. That's a completely natural process in math problems, especially as we get more into these college level math problems. If you try something and it doesn't work, you have to be willing to put in the time to persevere and then try something different. So in terms of our goals for this section, we finished our last goal. Over the last 2 videos, we've done some examples in which we evaluated some more challenging limits that involved the square root of some complicated stuff.